You're listening to Worth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our own Worth Electronic technical specialists who are going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. Happy New Year and welcome to 2022. Today we are discussing a fan favorite, and it's all about filtering in a switching controller. Switching controllers exhibit a residual ripple in their output voltage, which disturbs electronic devices, may actually cause electromagnetic interference, commonly known as EMI. Output filters are often used for interference suppression, which could exert an influence on the control loop. Compensation of the control loop may be required to prevent losses in output power. Irrespective of which switching controller topology is in use, the output current causes unwanted residual ripple through the parasitic series resistance, or ESR, and the parasitic inductance, or ESL, of the output capacitor. A relatively large residual ripple arises, which depends on the capacitor type selected, and it has different waveforms. For example, a common electrolytic capacitor causes a ripple voltage of up to several hundred millivolts, depending on the output voltage of the switching controller. Selecting a ceramic capacitor, the remaining ripple voltage may only be a few tenths of a millivolt. High residual ripple is undesirable, and it can disturb the electronic device. Special analog and high-frequency circuits require a stable, smooth, and clean supply voltage. However, the high-frequency component of harmonic oscillations on the output voltage cannot be overlooked, as this may lead to increased electromagnetic interference emission. Here, the output filter can reduce the residual ripple and filter out high-frequency components. In practice, the decision is usually made for an LC low-pass filter in order to reduce the residual ripple to a few millivolts and also to suppress high-frequency components. Figure 1 attached in this podcast shows this low-pass filter, which can be achieved with an unshielded coil, our WEE-PD2, and a conventional electrolytic capacitor. If a particularly clean output voltage is required, the LC low-pass filter is extended with a second-stage low-pass filter consisting of a ferrite and a capacitor. This type of two-stage output filter can be created pretty inexpensively with a WEE-PD2 coil and the WEE-MPSB surface mount ferrite. An example of this filter can be seen in Figure 2 attached in this podcast. L filter and C filter 1 actually act as a low-pass filter, which filters out the clock frequency of the switching controller and attenuates its harmonic oscillations. Further high-frequency components of the switching controller output voltage are then converted into heat by the surface mount ferrite, and together with C filter 2, their amplitude is attenuated. An output filter of this type reduces the residual ripple to a few millivolts, and it even allows sensitive analog circuits to be supplied. Above a certain switching controller output power, the output filter causes large direct current losses of the output power, and thus a reduction in the efficiency of the switching controller. The direct current resistance, or RDC, of the coils and ferrites now generates a significant voltage drop across the output filter, and therefore causes a reduction in the resulting output voltage. According to the dependence of the size of the coil, the DC resistance may be between a few milliohms and several ohms, and is therefore not negligible for high output currents. Even a surface mount high current ferrite can have an RDC of up to 0.04 ohms. To determine the actual voltage, the switching controllers, the output voltage is tapped from a voltage divider and is passed to the feedback connection of the switching controller IC. To reduce output voltage losses due to an output filter, There is the option of implementing the output filter in the control loop by determining the actual value of the output filter. However, the filter coil, ferrite, and the filter capacitors cause an unwanted phase shift, and this disturbs the stability of the control loop. This unwanted phase shift gives rise to a reduction in the amplitude and the phase margin. In extreme cases, it leads to instability, and the output voltage tends to oscillate. So in order to ensure stability, an amplitude margin of greater than 12 decibels and a phase margin of greater than 45 is necessary in practice, such that the converter does not oscillate on excitation. The control circuit is considered dynamically stable if the loop gain drops to 0 decibels before the associated phase shift has attained a value of negative 180. Here, the amplitude response of the loop gain should cross the x-axis, for example, at 0 decibels with 20 decibels per decade. A Bode plot of stable regulated step-down or buck converter shows an amplitude margin of 32 decibels and a phase margin of 56 degrees. If the stability criteria of a switching controller are not met with an output filter, compensation of the control loop is required to ensure a stable output voltage. This means the stability of the control section exerts an influence on the stability of the output voltage. So in the event of a voltage fluctuation at the input of the switching controller, the output voltage should remain stable. Analogously, in case of a sudden drop or rise of the output current, the output voltage should readjust quickly. This is what transient response means. Figure 3 attached in this podcast shows the transient response of a stable regulated switching controller, which is the yellow curve, with an output voltage of 5 volts and a sudden change in load from 0 amps to 1 amp, and we can see that in the green curve. A sudden change in load should lead to a rapid step response of the control circuit, which promptly regulates the output voltage of its target value. The step response should not cause too great an amplitude in the output voltage, otherwise electronic circuits could be destroyed by the overvoltage. Now, ideally, the output voltage should be promptly regulated to the target value following the step response without generating an overshoot or even generating ringing. Ringing during the compensation phase would be attributed to instability of the switching controller. If there is a fast step response and a timely compensation phase, the switching controller may be considered to be stable regulated. If the output filter is implemented in the control section is second order. This means the switching controller must be operated with a higher integration component, which attenuates the control section and slows it down. Complicated compensation of the control section is now required. The method of implementing the output filter in the control section is not recommended. The switching controller output voltage should be tapped directly at the switching controller output capacitor, maybe even before an output filter. It's recommended to select filter coils and ferrites with the lowest possible DC resistance in order to reduce DC losses in the output filter. Attached images are available in most podcast streaming networks. To view all images, visit www.we-online.com/podcast. To download the complete application note discussed today, visit Worth Electronic online at www.we-online.com/appnotes. You're listening to Worth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our own Worth Electronic technical specialists who are going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.